For decades, activated carbon has served as the undisputed industry standard for filtering industrial wastewater. Its primary asset is its staggering internal geometry. Engineers measure this capacity using the BET method, which calculates the total accessible surface area per unit of mass. Standard commercial activated carbon routinely exceeds 1,000 square meters per gram, the equivalent of an entire tennis court folded into a speck of dust. To manufacture that extreme surface area, producers rely on physical activation, hollowing out the raw carbon material by exposing it to intense thermal heating. But the heating process carries a steep cost. Extreme temperatures burn away unstable surface functional groups, the oxygen and hydrogen molecules attached to the edges of the structure. The resulting lattice is vast, but it is chemically stripped. A purely physical activation process yields a massive geometric sponge. When dealing with specific, stubborn industrial pollutants, empty space is not enough to capture them. A raw activated carbon particle operates on a strict structural hierarchy. Wide macropores act as entryways, channeling water into narrower mesopores, which finally terminate in tight micropores. When complex textile dyes or heavy metal cations, like mercury and cadmium, wash into this labyrinth, they encounter varying degrees of resistance. A fraction of these target molecules will become physically wedged inside the tightest micropores, trapped purely by spatial confinement. The rest of the pollutants drift through the wider macropores and mesopores. Without specific surface chemistry to anchor them, they exit the carbon matrix entirely. To stop these molecules, engineers use chemical modification. By deliberately bonding specific heteroatoms, like sulfur, oxygen, or nitrogen, back onto the carbon edges, they can tune the material's point of zero charge. This dictates exactly how the carbon reacts to the electrical properties of the surrounding water and the pollutants inside it. Populating the void spaces with targeted active sites transforms the carbon lattice into an engineered chemical trap. The first engineering challenge is isolating complex, highly reactive organic molecules, specifically anionic dyes used in textile manufacturing. A benchmark study by Orfau and colleagues isolated this variable by preparing 3 distinct carbon variants. They tested a baseline commercial carbon against 2 chemically modified extremes, one treated with nitric acid and another treated with thermal hydrogen gas. These treatments forced a divergence in surface polarity. The acid treatment yielded an acidic carbon matrix with a point of zero charge of 2.0. The hydrogen treatment produced a basic matrix, pushing its point of zero charge to 10.0. This data maps the experimental results. The charts plot the Langmuir capacity, the maximum amount of Rifafix red 3BN dye adsorbed, across the 3 carbon variants over time. The data reveals a performance disparity. The basic activated carbon vastly outpaces both the commercial baseline and the acidic variant. The primary driver is electrostatic attraction. The dye molecules possess a negative anionic charge. The high point of zero charge on the basic carbon creates a positively charged surface, pulling the dye out of the water. There is a deeper electronic mechanism at work. The basic treatment creates Lewis basic sites, packed with delocalized pi electrons. These electrons bind directly with the aromatic rings inside the dye molecules, securing them to the lattice. When extracting reactive organic dyes, tuning the surface charge and maximizing pi electron density dictates the adsorption capacity. Inorganic heavy metal cations, like cadmium, present a different behavioral profile in wastewater. Relying on broad electrostatic polarity is inefficient for these metals. They require specific molecular chelation sites, points where the carbon matrix can form direct coordinate bonds with the metal ion. To achieve this, researchers led by Macias Garcia developed a modification protocol. They treated commercial activated carbon with sulfur dioxide gas at 900 degrees Celsius. Baking carbon with sulfur dioxide causes the physical structure to degrade. The treatment resulted in a measurable reduction in both the total BET surface area and the internal porosity of the lattice. Yet the experimental isotherms produced a paradoxical result. Despite having the lowest available physical surface area, the sulfur dioxide-treated carbon increased cadmium adsorption by 70%. The treatment shifted the mechanism of capture. The carbon no longer traps cadmium through physical confinement in tight pores. Instead, the extreme heat forced sulfur complexes to bond directly into the carbon walls. These new sulfur heteroatoms act as targeted docking stations. They chelate the cadmium ions, pulling them out of the aqueous phase and locking them in place. Engineering a high-affinity chemical binding site generates a higher yield than simply maximizing physical space. Maximizing chemical capacity solves the capture problem, but material recovery creates a bottleneck. Saturated carbon must be physically extracted from the water. A study by Casetta addressed this by impregnating biomass-derived carbon with iron, forming crystalline magnetite and magnetite phases directly inside the pore structure. This creates magnetic activated carbon, or MAC. It is a dual-function composite engineered for chemical affinity and physical utility. To test its affinity, researchers mapped the docking mechanism between the composite surface and sunset yellow, a complex food dye. The iron oxides increase the density of acidic oxygen-containing groups. These functional groups lock onto the dye via rigid hydrogen bonding. Simultaneously, the flat carbon basal planes lying between the iron particles exert pi-pi dispersion forces, gripping the aromatic rings of the dye molecule. Once the carbon lattice reaches its maximum capacity, the iron phases perform their second function. The saturated carbon can be magnetically pulled straight out of the rapidly flowing wastewater stream, bypassing the need for slow mechanical filtration. Metal impregnation creates composite kinetics, binding pollutants through a complex electronic web while simplifying material recovery. The empirical data exposes the limits of untreated materials. Relying on massive physical surface area is a brute force filtration method that leaves highly toxic molecules in the water. To trap a pollutant efficiently, the carbon lattice must be laced with heteroatoms that exploit the electronic profile of the target. Extracting reactive, electron-rich organics requires basic chemical treatments that maximize pi electron density. Capturing heavy metal cations requires acidic treatments and sulfur complexes to force molecular chelation. And overcoming extraction bottlenecks requires metallic impregnation to enable parallel hydrogen bonding and rapid magnetic separation. The molecular identity of the target dictates the manufacturing protocol of the adsorbent, turning chemical tuning into a precise optimization task. Through deliberate chemical modification, engineers have moved wastewater treatment beyond physical filtration and into the precision molecular design of pollutant capture.